Okay, hey everybody, this is a supplemental video on chi-square tests. So this is one of the last topics that we're going to discuss, this and ANOVA. And to kind of motivate the chi-square tests, we're going to think back to a problem we had encountered earlier in chapter 8, where we were looking for a hypothesis test for a proportion for p, the probability of rolling a 1 on a six-sided die. And here we had a sample of 100 rolls, and we had 21 occurrences of 1. And we wanted to know, can we conclude the die is unfair? So the idea here was that we were something like a quality control engineer at a die manufacturer, and we think that we're manufacturing fair dice that come up, that say a 1 comes up on them about 1/6 of the time. And the question is, does that actually seem to be true for this particular die? Maybe if not, if we get far too many ones or far too few ones, we might think that there's a problem with the process. We might shut down our machine, recalibrate it, something like that. If we got exactly the right number of ones, that would make us happy. But of course, 1/6 of 100 isn't even a whole number. So we can't get exactly 1/6 of the rolls being ones. So then the question is, okay, there's going to be some sampling error. What's a tolerable error, right? 21 ones is a little higher than we'd expect. We might expect something like 16 or 17. We get 21. That's a little higher than we'd expect, but is that so much higher that we don't think that that happened by chance, just by sampling error, that there's some underlying problem that we want to investigate further? Or do we think that that's maybe close enough it could reasonably have happened by sampling error? So just to quickly go through this problem again, just to remember what the process looked like. This was a two-tailed test. P hat observed is 21 out of 100 or 0.21. And maybe we'll call it Q naught. We'll call this one P naught. Q naught is 5/6. And then like usual, we say assume H naught is true. So assume that the true probability of rolling a 1 for this die is 1/6. Then our random variable P hat is normally distributed. Because we assumed H naught is true, the mean of this normal is going to be 1/6. And the standard deviation of P hat is going to be, keep in mind we assumed H naught is true, so this is going to be root P naught Q naught over N. Our P hat observed, so 1/6 is about 0.167. Our P hat observed was 0.21, a little bit to the right. And remember, the idea here is that we say, okay, if we rejected for this sample, we would also reject for samples where we got more than 21 occurrences of a 1. If we reject for 21 occurrences, we'd reject for 22 or 23 or 24 anywhere in this right tail. But note that this is a two-tail test. So if I rejected for this much above my P naught, I'd also reject for this far below my P naught. So I'd also have a left tail that is equal in size. And so my p-value, which I'll write out as p-value here because we've already got the letter p being used for the proportion. This right tail is the probability, the random variable p hat, bigger than 0.21. And then we have a symmetric left tail that we have to take into account as well. So we have twice this probability. Or this is twice the probability that Z, so standardizing this, bigger than 0.21 minus the null hypothesized mean over the standard error, which turns out to be about 0.037. And this is twice the probability Z is bigger than 1.07. Probability Z is bigger than 1.07. We can look up off the normal table, and that's about 0.1423. Or this is about 28% for our p-value. In other words, if we rejected the null in favor of the alternative on the basis of this sample, we'd make a type 1 error about 28% of the time. And we're using, I suppose it's not officially stated here, but we were using alpha of 5% for our significance level, our maximum allowable type 1 error rate. So we say since the p-value is 28%, this is not less than 5% or alpha. In other words, our experienced type 1 error rate, if we made a rejection, is higher than the maximum allowable. Do not reject H naught. So in other words, on the basis of this sample, size 100 with 21 occurrences of a 1, we don't reject the null. We don't reject the die being fair. This could reasonably have happened just by chance, just by sampling error. We happen to roll a few extra ones this time, and maybe the die is still fair. But we see a pretty, so as far as the hypothesis test itself goes, this is a fine thing to do. But if we zoom out a little bit and think of why are we doing this hypothesis test, we see a pretty significant shortcoming here. And that's that we know nothing about what the distribution of 2s through 6s looks like, right? Maybe the 1s come up, roughly the amount that they should, but maybe the 2s come up way more often than they should, or the 5s come up hardly at all. We've only really looked at a single number on this die. So how do we expand this idea so that we can look at all the numbers on the die? Right? How do we kind of assess the entire die's fairness? One thing we might think is, well, maybe I could just do a hypothesis test just like this, but do it once for the 1s, and then go back and do it for the 2s, figure out how many 2s on this that I ended up rolling on this sample of size 100, and run the hypothesis test again, and do it for 3, 4, 5, 6. I could just do 6 of these hypothesis tests with the different values for X corresponding to which number on the die I'm looking at. And at first, that seems like a pretty good idea. The problem, though, is, well, this alpha is the maximum allowable type 1 error rate. In other words, we're going to make an error. We're going to reject H naught in favor of H1. We're going to call a die unfair when we really ought not to. We're going to do that 5% of the time. But if I make such a call 5% of the time on the basis of the 1s, but also 5% of the time on the basis of the 2s, and also 5% of the time on basis of the 3s and the 4s, 5s, and 6s, we can see that we're not going to have such a great type 1 error as we initially thought. We might have something, let's say ballpark figure of 6 times 5%, or something like, maybe in the 20 to 30% range for our actual type 1 error. And we think, so we're, in a sense, we think we're controlling our type 1 error at the 5% level, that we're not making this error more than 5% of the time, but we're really making it like 20 to 30% of the time, because we're doing so many of these tests kind of side by side. So this probably isn't a great approach. Now, maybe we could cut alpha to be a smaller number, and then after we do 6 tests, maybe Maybe we get a significance level we're happy with. Maybe we take an approach like that. Maybe we have some complicated decision criterion that if any one of the tests leads to a rejection, we don't think the die is unfair, but if two or more of the tests do, maybe then we conclude the die is unfair. But you can see how we're getting really hand wavy and really getting into kind of muddier and muddier territory here, trying to kind of force the use of this kind of a system where we're looking at one number at a time. So is there a better approach? And I think there is. I mean, better is always kind of a little bit subjective, but I think this is a better approach. Let's create a new hypothesis test where we consider all 6 outcomes at the same time. We consider the entire empirical frequency distribution all at once in one hypothesis test. So let's consider a die that has some true probability distribution. This is the actual for this die. P1 is the probability of rolling a 1, P2 the probability of rolling a 2, and so on. And for a fair die, we know that the probabilities are equal. In other words, P1 should be 1/6 if this was a fair die. P2 would be 1/6, and so on, and P6 would be 1/6 if this was a fair die. If it's not a fair die, then our alternative hypothesis is just that the null is not true. Or in this case, at least one of our probabilities is not 1/6. That would be an unfair die. So we give the benefit of the doubt, we give the null hypothesis to the fair die, and the alternative is that the die is unfair. But not just looking at a single number, a single, how many times we roll a 1, but looking at the distribution as a whole. Okay, so let's suppose that we have a sample of size 120. Here we're going to use numbers that kind of divide into 6 a little more nicely. So we have a sample of size 120. In other words, we took a particular die off the assembly line, or I suppose you don't assemble a die, the production line. And we rolled it 120 times. We counted up the number of 1, 2, 3, 4, 5, 6 that we got. If the die is fair, we would expect to get from 120 rolls 21s, 22s, and so on down to 26s. That would be kind of the theoretically perfect sample from a perfect die, from a perfectly fair die. We'd get, how did I get these 20s? Well, this is 1/6 times 120, right? The probability of rolling 1 times the number of rolls gives me the expected number of rolls that come up 1 that I would get from a perfect sample from a perfectly fair die, and so on. Now let's suppose that our sample, when we actually rolled 120 rolls, we observe this list of numbers here. In other words, we actually got 26 1s, 25 2s, and so on. And for future notation, we'll call these the expecteds. So like expected 1, expected 2, and so on. These are the expected number of, in this case, rolls that result in a 1 that we would get, the expected frequencies. And we'll call these the observed. So like O sub 1, O sub 2, and so on. These are the observed data from the actual real world, from the actual die that we're rolling. We got actually 26 1s, 25 2s, and so on. And now the question is, well, we have an empirical distribution from the real world versus a theoretical distribution that, again, the two don't look exactly the same. But could I reasonably get a sample distribution that looks like this from a theoretical distribution like that? Or are these two so far apart that I'd say that's unlikely to have happened by chance, by sampling error? And I think that really the underlying distribution is not that of a fair die, this one up here. Okay, so what does this process look like? How should we determine if the observed outcome is consistent with the null, or if we should reject the null in favor of the alternative? We'll use alpha equals 5%, again, just because that's kind of, a standard. But, you could use 10%, you could use 1%. We'll just use alpha equals 5% here. Now, something that we might think of doing is we might think that, well, if I look at the difference between observed and expected, if I take that difference, the bigger those differences tend to be, maybe the less confident that I am that it's a fair die, right? I mean, certainly if I got like 100 ones and 0 of anything else, I'd probably be quite certain that that die is unfair. The more the observed tend to deviate from the expecteds, the more certain that I am that the die is unfair, that I should reject the null in favor of the alternative. So if I look at something like observed minus expecteds, let's say, for instance, observed 1 minus expected 1. And if I look at these and I think, okay, if they're big, that's an indication that I should reject the null in favor of the alternative. Now, really, if the differences are big, they could be big positive or big negative, and I would like to somehow accumulate all of the differences. There's going to be one deviation for the rolls that ended up 1. There's going to be another deviation for the 2s, another for the 3s, and we've seen this strategy a couple of times already. So really, I'd like to investigate something like the squared deviations and then add them together. Right. If I get something like the sum of the squared deviations, then the larger that is, kind of the further away, in a sense, my observed data is from the expected data, or what I would expect of the data from the expected distribution. And the more confident I am that I should reject the null in favor of the alternative. So this is kind of the goal. Now, to make the math work out, we're going to do a couple of variations to this. So this is where we're going to eventually get to, something like that. But first we're going to note that, well, it would be super nice if we had a sampling distribution. If we had a sampling distribution for something related to these observeds, right? These are random variables. If I rolled the same die another 120 times, I'd probably get a different list of observeds. So these are random variables, these n observeds. And if I take, for instance, observed minus expected for, let's say, rolling 1, for instance, over the square root of expected 1, that seems like a strange thing to do, but the reason that we would do this is that this is approximately, there are some kind of approximations that go into this, but this is approximately normal. So I can construct a random variable based on these observeds that's approximately normal. One assumption for our test we're going to assume that, whoops, not that the expecteds up a level here. We're going to assume that the expecteds, that each of their frequencies are at least 5. Since they're each 20, we satisfy that assumption. But in other words, we're assuming that we have a sample that's large enough that we have at least 5, a frequency of at least 5 in each of the expected categories here. And we have 20 is bigger than 5, so that's fine. But if we had, a smaller sample, or if we had, an expected distribution where one of the probabilities was quite small, then we might have to have a larger sample to satisfy that assumption and be reasonably confident really in this approximation. So this is normal. If I square this, this looks like a normal squared. And if I square this, note that the squared hits the square root on the bottom, makes it go away. So I just have numerator squared over E1. And I'm going to have one of those for line 1, for line 2, all the way through line 6. If I add those up, what I have is a sum of squared normals. And remember that if I sum normal squareds, that gives me a chi-squared distribution. So this is the first big important idea here. The more that the observed data deviates from the expected frequencies, the larger this number is going to be. So larger numbers generate evidence in favor of H1, evidence to reject H0. So this is a right tail test. And what we would do then is we would compute a chi-squared observed by taking these observeds, these expecteds, and computing O1 minus E1 squared over E1, O2 minus E2 squared over E2, add those together, and so on. So what is my null hypothesis? My null hypothesis is that the die is fair. In other words, that the probability of rolling a 1, 2, 3, 4, 5, 6 are all 1/6. And my alternative hypothesis is not the null. In other words, that at least one of the probabilities is not equal to 1/6. Get a little more room here. This is a right tail test. There's chi-squared. And remember, what is the idea? The idea is that I compute a chi-squared critical. I compute a critical number, or look up a critical number, I suppose. I compute chi-squared observed. If chi-squared observed is less than chi-squared critical, this is a right tail test, then we do not reject H0. We don't have a big enough deviation between the two distributions to conclude the die is unfair. On the other hand, if we were to compute chi-squared observed, and it was to the right of chi-squared critical, we would reject H0 in favor of H1, reject H0 in favor of H1, and we would conclude the die is unfair. Okay, so then what is chi-squared observed? And what is chi-squared critical? Let me change my share here. Okay, and I think I forgot to mention that degrees of freedom is n-1. So here, where n is the number of frequencies that we have. So not 120, but 6, right? In other words, I could choose, say, these 5 in a sense any way that I want. I have to have a total frequency of 120. If you leave me one frequency, one last frequency to kind of make things work out right, then you can choose the other 5 or the other n-1 more or less any way you want. I mean, you can't choose one of them to be 130 or something, but there's 5 lines that have this degree of freedom to them that can be chosen different ways. And then once those are chosen, the last one is fixed. So what am I looking at? I'm looking for a chi-squared number for chi-squared critical with 5 degrees of freedom and with an area to the right of 5%. So I'm looking for a chi-squared number, 5 degrees of freedom, area to the right of 5%. That's 11.071. And then for chi-squared observed, get Excel to open up here. We use Excel for this calculation just so that we don't have to do quite so much by hand. For chi-squared observed, what do I want? Well, I have my observed and expected, so let me just make 2 columns for those. So my observeds are 26, 25, 9, 19, 22, and 19. And let's just check that those add up to 120, and they do. So that's our sum. Expected is 20 for each of them. And then I want my observed minus expected squared over expected. So let me do that. Observed minus expected squared over expected. Or this is going to be this minus this squared over this. I have one of those numbers for each of my 6 rows. And then I want them to add them together. So this will be my chi-squared observed. So I add those together. Did I get them all? The thing popped up kind of in the middle. Looks like I got them all. Of 9.4. So my chi-squared observed, 9.4. My chi-squared critical is 11.071. My chi-squared observed is indeed to the left of chi-squared critical. This is a right tail test. Remember, because we get bigger chi-squared observed when we have bigger deviations between the observed and expected data, or when there's more evidence that the die is unfair. This is a right tail test. Chi-squared observed is not to the right of chi-squared critical, so we do not reject. In other words, such a distribution in the sample could reasonably have occurred just by sampling error. Then we can ask, what about, we have a different die that came off maybe a different assembly line. We roll it 120 times, and we get these observed data. I mean, getting 0 6s in 120 rolls is pretty suspicious. So we might have a gut feeling that this one probably is going to be unfair, but let's look at these observed. This is still, similar setup as up here. We still have 120 rolls. We're still testing at the 5% level and all of that. So really all this changed is our observed numbers. So we can just put these numbers in instead. 7, 38, 30, 31, 14, and 0. Keep in mind the same picture applies here. So I might actually just select all of this and copy it down just to save a little bit of writing. So most of this applies. Our chi-squared observed is going to be a different number. and whether we reject or not is going to be different. But in this case, we have chi-squared observed of 57.5 versus the chi-squared critical of 11.071, still a right tail test. But comparing to 11.071, 57.5 is way out to the right. So we say since chi-squared observed is bigger than chi-squared critical, we reject H0. We conclude that the die is unfair, and maybe we want to say shut down this production line and investigate further or recalibrate the machine or something like that. Okay. Let me switch the share back to just this screen. All right, so famous use of the chi-squared goodness of fit test, which is what this test is called. Famous use is Mendel's P experiments, or experiments kind of like these. That's not to say that Mendel used this technique, but it's a technique that you see in a lot of bio classes and those kind of more modern approaches to this type of experiment. So what's the idea here? The idea, so if you don't know, Gregor Mendel is the monk from, I don't know, a few hundred years ago who really kind of started the idea of genetics. He kind of started the idea that there are certain traits that are passed on from generation to generation and they kind of persist across generations. And he really studied this with a lot of these experiments with different types of plants and vegetables and things like that. So the idea of Mendelian inheritance is, let's say that we have mom and dad. We're going to be talking about pea plants, but we can still kind of envision a mom and dad and pretend that we have mom and dad because it's a little easier to think about. And let's say that there's one trait that we're interested in. Let's say the trait yellow versus green. So the color of the pea. Now mom has, let's just say that the gene controlling the color of the pea, let's say it's a single gene, and let's say it's on chromosome 1. So mom has 2 copies of chromosome 1, and dad also has 2 copies of chromosome 1. Let's just say, for instance, that mom has on 1 copy of chromosome 1 a gene that suggests the color yellow. So she has the yellow allele. And on the other copy of chromosome 1, she has the green allele. So that copy of that gene, of that chromosome, has a gene on it that would make the color green. And then let's say the dad has something similar. So when they have offspring, well, the offspring end up getting 2 chromosomes as well, and there's kind of 4 here. What happens? Well, essentially mom picks one of her chromosomes to give and gives it to her offspring. So she could pick yellow, or she could pick green to give to her offspring. And likewise with dad independently picks, in a sense, whether to give the offspring his first copy or second copy, his yellow or green. So mom could pick yellow and dad picks yellow. Mom could pick yellow, dad picks green, or vice versa. We typically write this way. So in other words, the offspring could get yellow from mom, yellow from dad, yellow from mom, green from dad, green from mom and green from dad, or green from mom and yellow from dad. And these would be equally likely under Mendelian inheritance. Okay, so if we looked at something a little more complicated, What if we looked at yellow versus green as well as smooth versus wrinkled? So then we need a little bit bigger of or a little higher dimensional space to work in. And again, I know these are pea plants. We're just going to call them mom and dad because that's just easier to talk about than saying like parent one versus parent two or something like that. So mom has, as far as the color goes, she has one yellow allele and one green allele. And as far as smoothness goes, she has one smooth allele and one wrinkled allele. So this is important that, this was set up this way. This experiment is set up this way so that you have what's called this dihybrid cross. So this is an assumption that we're making about mom and dad. That mom has one yellow allele, one green allele, and also maybe on a different chromosome, one smooth allele and one wrinkled allele. So mom could give yellow and smooth. It's actually a similar process to over here where we just have mom like chromosome 1 versus chromosome 2 almost. Mom could give yellow for color and smooth for texture. Mom could give yellow and wrinkled. Mom could give green and smooth or green and wrinkled. And then dad has the same phenotype, or the same genotype, I should say. Dad has the same genotype, so his results are going to be the same. So we see that we have 16 different possible genotypes for the offspring. Right? For instance, mom could give yellow smooth, we could be in the first column, and dad could give green wrinkled, we could be in the bottom row. There are 16 equally likely boxes we could be in, 16 equally likely genotypes that the offspring could get. Now, there's one more important idea here, and that's the idea of dominance versus recessiveness. So in other words, if an individual has, say, one yellow allele and one green allele for peas, the pea will be the color yellow. So yellow yellow gives yellow, yellow green gives yellow, green yellow gives yellow, and green green is the only one that results in a color of green. So we would say that green, the green trait is recessive and the yellow trait is dominant. So if either of the chromosomes have a yellow allele, the color will be yellow. If they both have a yellow allele, the color will be yellow, but only if they both have green and there's like no yellow allele anywhere, then the green trait kind of shines through. And similarly with smooth and wrinkled, smooth is dominant, wrinkled is recessive. So in this grid, we're going to put down phenotypes. So Mendel, of course, didn't have the sequencing technology that we have today, of course, that's only been developed in the last 50, 70 years or so. So Mendel could look at the phenotypes. He could look at the color of the peas and look at the smoothness of the peas and make some inferences. So what phenotypes would we get here? What would the look or the trait of the pea be if we had the top left box here, the top left genotype? Yellow smooth from mom and yellow smooth from dad. Well, then the phenotype is yellow smooth. The offspring gets 2 yellows and 2 smooths, so of course yellow smooth. If we go to the right one, the color is still yellow, and smooth versus wrinkled, but smooth is the dominant trait, so smooth is the one that comes up as the trait that you would actually see on the phenotype. Yellow versus green, yellow wins, and smooth versus smooth is of course smooth. And yellow smooth versus green wrinkled, yellow smooth wins in both cases. So in the case that one parent gives both dominant genotypes or both dominant alleles, then just that whole row or column becomes those dominant phenotypes. So we can go down here as well and say the same thing. Mom's yellow and mom's smooth is going to kind of trump anything that dad throws at the situation. Now going across the second row down, yellow is always going to win over green. But then dad gives wrinkled. Now in this box here, mom also gives wrinkled. So we have a wrinkled. That P would have a wrinkled texture. Wrinkled versus smooth is going to be smooth. And wrinkled versus wrinkled again is going to be wrinkled. Third row. Well, dad gives a smooth, which is dominant. So the phenotype for texture will always be smooth in this row. But dad gives green, which is recessive. So green against the yellow is going to give yellow. Green against green in either case gives green. And the last row, green wrinkled from dad. So basically whatever mom gives is what we're going to end up with. The yellow is dominant over the green, and the wrinkled, because we have wrinkled, is what shows up in the phenotype. Mom's green meets dad's green, and the offspring is colored green. Smooth versus wrinkled, smooth is dominant. Green wrinkled versus green wrinkled, there's our green wrinkled. Okay, so we see a lot of yellow smooths, so let me circle those. So these are all yellow smooth phenotype. Let me get myself a little more room down here. So I see 9 of these boxes that are yellow smooth. I don't have a ton of colors, so I'll go through and just put diamonds around the yellow wrinkleds. I see 3 yellow wrinkleds. I see 3 green smooths. And I see 1 green wrinkled. So in other words, if Mendelian inheritance is correct for these traits, then I'd expect to see a ratio of 9:3 to 3:1 for these 4 different traits. And remember, this is 16 equally likely boxes. So we'd expect to see probabilities of 9/16, 3/16, 3/16, and 1/16. These would be our expected probabilities for a dihybrid cross under Mendelian inheritance. Okay, so let's consider an experiment where we maybe perform such a dihybrid cross, and we get this experimental data. So we actually do the experiment, we grow a bunch of peas, and we see that we got 65 plants were yellow smooth, 19 were yellow wrinkled, 9 were green smooth, 7 were green wrinkled. And we want to know, should we reject the hypothesis of Mendelian inheritance? Should we reject the null that these are actually the probabilities of these phenotypes? Okay, so what do we do here? How do we do this calculation? Well, the first thing we need to know is what is our total number of plants? So we have 65 plus 19 plus 9 plus 7 gives me 100. So I have a total of 100 plants that I observed and that I actually got these phenotype data for. So then if Mendelian inheritance were true, if the null is true, and if I had like a perfectly representative sample, what would I expect for yellow smooth or green wrinkled or whatever? Well, I would expect, for instance, 9/16 times 100 for the frequency for yellow smooth, right? 9/16 times 100, that should be the number of yellow smooths, which would be 56.25. Now, just the note, of course, like we're never actually going to get exactly 56.25 plants that are yellow smooth. We might get 56 or 57, not going to get 56.25. But in this experimental frequency distribution, or sorry, expected frequency distribution, it's fine to not have round numbers, right? We just put the 56.25 in there and leave it at that. The next one, 3/16 times 100 is 18.75. The same, of course, for the next one that has the same probability as the second one. And then 6.25 for the last. 1/16 times 100. And then if we run our hypothesis test, we want to take our observed minus expected squared over expected for each of these. Add them together. And this gives me chi-squared observed. And then I calculate chi-squared critical. Alpha equals 5%. Degrees of freedom are 4 minus 1 or 3. And remember, this is a right-tailed test, right? Larger deviations between the observed data and the expected data should generate a rejection. So large values of chi-squared observed should generate a rejection. So this is a right-tailed test. Okay, so let me switch my share back again. So for chi-squared observed, I'll just kind of zero out these ones. Oh, I guess that made Excel sad. So I need to change my observeds to these 65, 19, 9, and 7. And my expecteds to 56.25, 18.75, 18.75, and 6.25. So I see that these two are quite close. This one's maybe a little further away, but these three are pretty close. But I see that my chi-square observed is 6.52. I also need to look up chi-squared critical. Again, right tail, 5% area, degrees of freedom 3. So area to the right of 5% with 3 degrees of freedom, that's 7.815. So I have a chi-squared distribution, my chi-squared critical, 7.815. My chi-squared observed, 6.52. that is not to the right of chi-square critical, I do not reject. This observed frequency distribution is not sufficiently far away from what we would expect under Mendelian inheritance for us to say that this is unlikely to have just happened by chance, by sampling error, and that we should reject the hypothesis of Mendelian inheritance for these traits. So we would proceed forward under the hypothesis of Mendelian inheritance for these traits. Okay, and then we have a test that is sometimes or often kind of treated separately from chi-squared goodness of fit, but it really is a very similar idea, and that's the chi-square test for independence. We've talked quite a bit before about independence and really actually how important it can be for probability calculations. And on the flip side, that if we assume independence and we don't have it, it can really mislead us. So it would be really nice if we had two variables with some data to be able to get an idea of whether we think those two variables are independent or not. So let's let x and y be two variables, or sometimes these are called factors. And suppose that they have R and C outcomes, or sometimes these are called levels. So unfortunately, when we get into things like some of these tests or ANOVA, there's some different wording that's used for different pieces of the analysis, I suppose, here. And part of that is that these tests are used by just a very wide range of folks, across the biological sciences, the hard sciences, the social sciences, used by statisticians, and everybody kind of tweaks the wording a little bit to kind of fit their needs a little bit better. So there can be different different wording or different ways of discussing the same thing in different areas. Okay, so what's the idea here? The idea here is we have two variables. We have one variable that has a bunch of different possible outcomes, as does another variable. So I could draw a grid like this. And the idea is that we have one variable, what did I call it? So I said respectively up here, so I guess I have to be careful about my letters. So X variable has our outcomes, or there are rows here. So this would be like outcome X1, X2, 3, 4, 5, X6. Whatever it is that we're measuring, whatever it is that we're interested in the variable X. So this might be, what color shirt somebody's wearing or something like that. And then variable Y, it has outcomes as well. So similar thing, maybe what color pants the person's wearing. 1, 2, 3, 4, 5, 6, Y, 7, let's say. So here there are C columns. Now, these rows and columns result in row totals So in other words, if I had different colors of shirts and different colors of pants, and I say, okay, this person has a red shirt and blue pants, that would locate them in a specific box here. I would do this for a bunch of people, and I would have different numbers in all these different boxes for how many people had red shirt and blue pants, or black shirt and white pants or whatever it may be. So there will be row totals for whatever I said X was. I think X was color of shirts. So this would be like total people with red shirts and total people with blue shirts or whatever, regardless of their pants colors. There would also be column totals. So there would be, a certain number of people who had blue pants, regardless of what shirt color they were wearing. So these would be column totals. And then kind of in the corner over here, we'd have a grand total. If we added up all the columns, we get a number, or if we added up all the rows, we'd get the same number. This is grand total, or this is the sample size. Now, importantly, these are fixed. So let me see if I can do a decent job of highlighting these. So we take these to be fixed. And now when I compute degrees of freedom, in other words, how many boxes in the interior here could I pick however I want and still allow myself enough flexibility that I could meet all of these column and row totals? And the answer is, to meet the column totals, I could pick, to meet column total 1, I could pick the first 5 X's any way I want, as long as I leave myself X6 to adjust to make that column total work out. So to make the column totals work out, I can use all but one of the rows. I could choose those numbers essentially however I want, as long as I leave that last row in order to make my column totals work out. But the same is true of the rows and the row totals and the columns. I could choose the first 6 out of 7 here of the columns any way that I want. And if I leave myself one at the end, I can ensure that the row totals work out. So I can choose any of these any way that I want. These can be free to change, as long as I leave one column and one row to give me enough flexibility to meet all of those row and column totals, which are fixed. Or in other words, I can choose C minus 1 columns and R minus 1 rows however I want. What are my degrees of freedom? How many boxes can I choose? R minus 1 times C minus 1. Right? I can choose all of the green boxes, and that's R minus 1 times C minus 1. In this case, it would be 6 times 5 or 30, and you can count and see that there are 30 green boxes. And then what are my hypotheses? My null is that X and Y are independent. And my alternative is that X and Y are not independent, or that they are dependent. Okay, so suppose we're interested in knowing whether clothing type is independent of color choice. And we want to know, is this sample consistent with independence of these two variables? So suppose we get the following sample. So we get shirt versus pants for type, and for color, we get red versus green. Since it's near Christmas, we'll use red and green, I suppose. And suppose we observe these numbers. So this is observed. This is data we've collected from the real world. Now what we could do is, in essence, create an expected distribution if these were independent. And then we can look at concordance between the two. I'm actually going to move this down just a tad. So I could come over here and I could say, well, there's going to be some expected distribution if these were independent. So shirt versus pants, red versus green. Now, I don't know what numbers go in here right now, but this is where those row and column totals become important. So let's come over to our observed data here. And let's say, okay, how many people total had a red shirt on? Or sorry, how many people total had a red piece of clothing on? 20. So 3 red shirts plus 17 red pants. How many people total had a piece of green clothing on? 67 plus 13. So that's 80. So we had 20 red and 80 green. The grand total is, of course, 100. And then if we look at the types, how many people total, I guess, had a shirt on? I mean, maybe my analogy is starting to break down here, but how many of the observed people had a shirt that was one of these two colors, I suppose is a better way to put it. 70. And how many had pants that were one of these two colors? 20, 30. So these are my column totals and my row totals. Now I'm going to copy these over. These are what I'm taking to be fixed. And now I'm saying, okay, for a sample of size 100, where there were 20 folks with red clothes and 80 folks with green clothes, or 70 with festive shirts and 30 with festive pants, what would I expect each of these 4 boxes to be, right? Really, all that we're doing is we're doing what we kind of previously did in 1 dimension, so to speak, with just 1 variable, and we're just doing it for 2 dimensions and 2 variables. So remember, with independence, probability of A and B is probability of A times probability of B. Or in other words, this box up here should look something like 70 times 20. Now we do have to be a little careful. If we have 100 in the row totals and 100 in the column totals, and we just multiply everything together, we'll get like 10,000. We'll be kind of over counting by a factor of n, our sample size. So we have to divide by 100. So it's kind of like saying 70 over 100 or 70% of these 20, right? 70 over 100 times 20, 70% of the 20 should have red shirts, and then 30% of the 20 should have red pants. Right? That's effectively what we're saying. And then 70% of the 80 should have green shirts, and 30% of the 80 should have green pants. And if we calculate each of these numbers, we get 14. I knew that it was going to make that a 4 into a 9. We get 6. We get 56. And 24. And you can really see where this degrees of freedom is coming in, right? Once we figured out 14 from the 70 times 20 over 100, we really could have just subtracted from the row and column totals to get the rest, right? 14 plus 1 makes 20. That's got to be 6. 14 plus what makes 70? That's got to be 56. And then, 6 plus what makes 30? That's got to be 24. So 14 was only, but we can only really choose one of these boxes kind of any way we want. And then to meet the row and column totals, everything else is locked in. Okay. So what do we think chi-squared observed is going to be? Well, again, we have an observed distribution and an expected distribution. It's going to look like observed minus expected squared over expected. So for the red shirts, the observed frequency was 3. The expected, if they were independent, is 14. Observed minus expected squared over expected. Same thing for the red pants. Observed minus expected squared over expected. Same for the green shirts. And for the green pants. Okay, let me switch my share back again here. So essentially, I can come over here and I can just kind of hijack this same Excel spreadsheet. So I have 3, 17, 67, and 13. And then I just have to make sure I go in the right order. So 14 goes with the 3, the 6 goes with the 17, the 56 goes with the 67, and the 24 goes with the 13. So my chi-squared observed is something like 36. My chi-squared critical, and again, we'll use the 5% level. I guess I didn't say it in the problem statement, but we're just using that as the default. My degrees of freedom are row minus 1 times columns minus 1. My degrees of freedom is only 1. And again, we kind of saw that once we had got 14 in here, everything else was predetermined by the row and column sums. So I'm going to go to my chi-squared distribution, 5% area to the right, just like before, but with 1 degree of freedom. That's 3.841. That's chi-squared critical. Chi-squared observed is 36. That's certainly far to the right of chi-squared critical. We'd reject H naught, and we would conclude that color choices for pants versus shirts are not independent, or color choice versus clothing type is not independent. Okay, so I do have one last example, and this is just purely on Excel. One more example of independence. So we have an example of college enrollment by sex and full-time status. And we're interested in whether we think that the sex of one of our students versus their full-time or part-time status are independent or not. Do we think there's a relationship between the two? So this is our actual observed data. This isn't for CCAC, this is for some other data set. So we have some males and some females enrolled. So 9,300 males, 11,000 females. We have some full-time and part-time folks, right? 14,000 full-time and 6,000 part-time. And they break down this way for our particular institution. Not ours, but for this hypothetical one that we're talking about. Now, again, what stays consistent is the row and column totals. So we're going to fix the row and column totals. And then we're going to ask, okay, if they were independent, what numbers would we expect here? Instead of 67, 68, we would expect 65, 20. We'd expect the product of the row total and the column total divided by n, or in other words, we'd expect this proportion, 14,000 out of 20,000, of these 9,000 folks to be here. And we'd expect this proportion, 6,000 out of 20,000, that proportion of the 9,000 folks to be part-time. So we do that for each of these four. And then we do the same thing, observed minus expected squared over expected for each of those four cells gives me these numbers. And adding those up gives me chi-squared observed of about 56. That's in relation to a chi-squared critical of 3.84. And we could get that out of Excel this way. Chi-squared inverse right tail, 5% area with 1 degree of freedom. Again, the degrees of freedom are rows minus 1 times columns minus 1. In this case, is also 1 degree of freedom. Since chi-squared observed is bigger than chi-squared critical, we can reject H0 and conclude that full-time status and sex of enrollee are not independent variables. Okay, so hopefully that gives you some insight into why we want to do such a chi-square test instead of just doing a whole bunch of Z or T tests, or I suppose in this case, Z tests. And then how to actually carry those out in maybe a couple of different scenarios. So that wraps up the chi-squared test supplement, and then I'll post a supplement on ANOVA a little bit later.